Today we're looking at Leetcode problem 2780, minimum index of a valid split. The problem defines an element x in an array arranged by length m as an element that appears more than m/2 times. We are given a zero-indexed integer array nums, which is guaranteed to have one dominant element. Our task is to split this array, nums at an index I, into two non-empty subarrays, nums, 0, I and nums, plus 1, n1. The split index I must satisfy 0 less than equals I less than n1. A split at index I is called if both resulting subarrays, nums, 0 and nums, plus 1, n1, share the same dominant element. We need to find the minimum index I that results in a valid split. If no such valid split exists, we should return -1. Let's walk through the first example. The input is nums equals all theta, all theta, all theta, all theta, all theta, n is 4. The length n is 4. The possible split indices I are all theta, villainty, all theta, all theta, all theta. Let's check I equals 0, left subarray, 1, right subarray, 2, 2, 2. In 1, the dominant element is 1, count 1, length 1, 1, 2 greater than 1 is false. Wait, the definition is strictly greater than half, so 1, 2 greater than 1 is true. In 2, 2, 2, the dominant element is 2, count 3, length 3, 3, 2 greater than 3 is true. The dominant elements, 1 and 2, are different. So I equals 0 is not a valid split. Let's check I equals 1. Left subarray, 1, 2. Right subarray, 2, 2. In 1, 2, length is 2. Half the length is 1. No element appears more than once. No dominant element. Not a valid split. Let's check I equals 2. Left subarray, 1, 2, 2. Right subarray. In 1, 2, 2, length is 3. Half the length is 1.5. Element 2 appears twice. Since 2 greater than 1.5, element 2 is dominant. In 2, length is 1. Half the length is 0.5. Element 2 appears once. Since 1 greater than 0.5, element 2 is dominant. Both subarrays have the same dominant element, which is 2. This is a valid split. Since we are looking for the minimum valid index, and we found I equals 2 is valid, the answer is 2. In the second example, nums equals 2, 1, 3, 1, 1, 1, 7, 1, 2, 1. The length is 10. The dominant element in the whole array is 1. It appears 6 times, and 6, 2 greater than 10. The output is 4. Let's verify this split. If I equals 4, the left subarray is 2, 1, 3, 1, 1. Length 5. The right subarray is 1, 7, 1, 2, 1. Length 5. In the left subarray, 2, 1, 3, 1, 1. Element 1 appears 3 times. The length is 5. Is 3, 2 greater than 5? Yes. 6 greater than 5. So 1 is dominant. In the right subarray, 1, 7, 1, 2, 1. Element 1 appears 3 times. The length is 5. Is 3, 2 greater than 5? Yes. 6 greater than 5. So 1 is dominant. Since both subarrays have the same dominant element, which is 1, the split at index 4 is valid. The problem statement implies that this is the minimum such index. We'd need to check indices 0, 1, 2, and 3 to confirm they don't yield a valid split, but we'll trust the example explanation for now. Before diving into code, let's think about the core requirement. We need to find a split point I, such that the same element is dominant in the left part, nums from 0 to I, and the right part, nums from I plus 1 to n1. A key observation simplifies this significantly. The problem statement guarantees that the original array nums has exactly one dominant element. Let's call this dominant underscore element. Now consider a valid split at index I. Let the common dominant element in both subarrays be x. Can x be different from the original dominant underscore element? If x is dominant in the left part nums, 0i, its count in the left part, let's say count underscore left x, satisfies count underscore left x2 greater than I plus 1. If x is dominant in the right part, nums, plus 1, n1, its count underscore right x satisfies count_right x2 greater than n minus I plus 1. Adding these two inequalities, count_left x2 plus count_right x2 greater than I plus 1 plus n I1. Count_left x plus count_right x2 greater than n count_overall del mem mess time narandal x2 greater than n. This means that x must also be dominant in the original array nums. Since the problem guarantees only one dominant element exists overall, x must be equal to dominant_element. This insight is crucial. We don't need to check every possible element at each split. We only need to check if the original dominant_element is dominant in both subarrays. So the refined plan is 1. Find the dominant_element of the entire array nums. 2. Iterate through possible split indices I vount $3. For each I, check if dominant_element is dominant in nums 0 and dominant_element is dominant in nums +1, n1. Return the first I that satisfies both conditions. The first approach uses a hash map to efficiently count element frequencies. It conceptually involves two passes over the data. In the first pass, we iterate through the entire nums array. We use a hash map, like a Python dictionary, to store the count of each number. While doing this, we can keep track of the element with the highest frequency seen so far. Since we're guaranteed a dominant element, by the end of this pass, we'll know the dominant_element and its total underscore count in the whole array. In the second pass, we iterate through all possible split points, index I, from 0 up to n2. Remember, both subarrays must be non-empty. As we iterate from left to right, we maintain a running count, let's call it left_count, of how many times we've seen the dominant_element in the range nums, 0, I. For each index I, we know the left_count. We can easily calculate the count of the dominant_element in the right subarray, nums, +1, n1, by subtracting the left_count from the total count we found in the first pass. Let's call this right_count. So right_count equals total_count, left_count. Now, we just need to check if the dominance conditions hold for this split index y. First condition, is dominant_element dominant in the left subarray nums, 0 I. This means checking if left_count2 is strictly greater than the length of the left subarray, which is I plus 1. Second condition, is dominant_element dominant in the right subarray nums, +1, n1. This means checking if right_count2 is strictly greater than the length of the right subarray, which is n1-I. If both these conditions are true, we've found a valid split. Since we are iterating I from 0 upwards, the first time we find such an I, it must be the minimum valid index. We return I immediately. If we go through all possible split indices I from 0 to n2, and don't find any that satisfy both conditions, it means no valid split exists, so we return -1. Here's the Python code implementing the hash map approach. First, we get the length n of the input list nums. We use collections.Counter nums, which efficiently creates a hash map, dictionary, mapping each element to its frequency in nums. We then iterate through the items, element, count pairs, in this counts map. The condition count2 greater than n checks for dominance. Since we're guaranteed exactly one dominant element, as soon as we find it, we store it in dominant_element, store its count in total_count, and break the loop. Next, we initialize left_count to 0. This variable will track the count of the dominant_element in the left subarray as we iterate. We loop through I from 0 to n-2. Inside the loop, we first update left_count. If the current element nums is the dominant_element, we increment left_count. Note that this left_count now represents the count in nums, 0, I or. We calculate right_count simply as total_count, left_count. Then we check the two dominance conditions. Is _dominance_left checks if left_count multiplied by 2 is greater than the length of the left subarray, which is I plus 1. Is _dominant_right checks if right_count multiplied by 2 is greater than the length of the right subarray, which is n1-I. If both conditions is _dominant_left and is _dominant_right are true, we've found the smallest valid split index I, so we return I. If the loop completes without returning, it means no valid split was found, so we return -1. Let's analyze the time and space complexity for this hash map approach. For time complexity, first, creating the frequency map using collections.Counter, nums, takes linear time, proportional to the number of elements n, so that's on. Finding the dominant element involves iterating through the entries in the frequency map. In the worst case, there could be on unique elements, so this step could take up to on time. The second main loop iterates from I equals 0 to n2. Inside the loop, we perform a constant number of operations, an increment, a subtraction, 2 multiplications, 2 comparisons, and a potential return. So, this loop takes on time. Adding these up, on plus on gives an overall time complexity of on. For space complexity, the primary extra space used is for the hash map counts. This map stores the frequency of each unique element in nums. If there are k unique elements, the space complexity is O over a k. In the worst-case scenario, all elements in nums could be unique, meaning k could be up to n. Therefore, the space complexity is on, in the worst case. Other variables like n, dominant underscore element, total underscore count, left underscore count, right underscore count, use constant, O1, space. So the dominant factor for space is the hash map, giving us on space complexity. Now let's look at a more optimized approach, particularly in terms of space complexity. We can use the Boyer-Moore voting algorithm. The Boyer-Moore algorithm is famously used to find the majority element, an element appearing more than n/2 times, in an array in linear time and constant space. Since our dominant element definition is slightly different, but still relies on a majority, Boyer-Moore can find the only possible candidate for the dominant element. Here's how it works. Initialize a candidate variable and a count to 0. Iterate through nums. If count is 0, set the current element as the candidate and set count to 1. If the current element is the same as the candidate, increment count. If it's different, decrement count. After iterating through nums, the value stored in candidate is the only element that could be dominant. However, Boyer-Moore only gives us a candidate. We still need to verify if it is dominant and find its total count, so we need another pass through nums, just to count the occurrences of the candidate. Let's call this total underscore count. We then verify if total underscore count 2 greater than n. The problem guarantees a dominant element exists, so this check should always pass for the candidate found. After finding the candidate, which we now know is the dominant underscore element, and its total underscore count, the rest of the logic is identical to approach 1. We iterate through the possible split indices I from 0 to n2. We maintain the left underscore count of the dominant underscore element in nums, 0i. We calculate right underscore count equals total underscore count, left underscore count. We check the dominance conditions. Left underscore count 2 greater than I plus 1, and right underscore count 2 greater than n, 1i. If both hold, we return I. If the loop finishes, we return -1. The main advantage here is that finding the candidate and its total count can be done without using a hash map, reducing the space complexity to O1. The time complexity remains On, because we still perform passes through the array. Here's the Python code implementing the Boyer-Moore-based approach. First, we find the candidate using the Boyer-Moore algorithm. We initialize candidate and count. We iterate through nums. If count is 0, the current num becomes the new candidate, and count becomes 1. If num matches the candidate, count increases. Otherwise, count decreases. After this loop, candidate holds the potential dominant element. Next, we perform a second pass to get the actual total underscore count of this candidate element, which we now confirm is the dominant underscore element. We initialize total underscore count to 0 and iterate through nums again, incrementing total underscore count whenever we encounter the dominant underscore element. The third part is exactly the same as in approach 1. We initialize left underscore count to 0. We iterate I from 0 to n2. We update left underscore count based on nums. We calculate right underscore count equals total underscore count, left underscore count. We check the dominance conditions left underscore count 2 greater than I plus 1, and right underscore count 2 greater than n1-I. If both are true, we return I. Finally, if the loop completes without finding a valid split, we return -1. This code achieves the goal using only constant extra space, aside from the input array itself. Let's analyze the complexity for the Boyer-Moore-based approach. Time complexity. The first step, Finding the candidate using Boyer-Moore involves a single pass through the array nums. This takes on time. The second step, counting the total occurrences of the candidate, requires another pass through nums. This also takes on time. The third step involves iterating through possible split indices I from 0 to n2. Inside this loop, we perform constant time operations. This loop takes on time. The total time complexity is on plus on plus on, which simplifies to on. Space complexity. In this approach, we are only using a fixed number of variables to store the candidate, counts, indices, etc., regardless of the size of the input array nums. We don't use any auxiliary data structures like hash maps whose size depends on n, or the number of unique elements. Therefore, the space complexity is O1, or constant space. This is an improvement over the first approach's on space complexity. That's how you can solve the minimum index of a valid split problem using both a hashmap approach and a more space-efficient Boyer-Moore-based approach. Both run in linear time, but the second one uses only constant extra space. Remember the key insight. The dominant element in both valid subarrays must be the same as the dominant element of the original array. This greatly simplifies the checking process. If you found this explanation helpful, please like the video, subscribe to the channel, and leave a comment below. Let me know if you have any questions or suggestions for future problems you'd like to see covered. You can also help me continue making these videos by donating at buymeaboba.com. The link is in the description below. Thanks for watching.